Welcome to Lyons Township High School. Today we're going to do an example involving electromotive force, EMF, or voltage, involving a circuit that has a couple things going on. So the first thing that I would suggest you do right now is I would suggest you copy this circuit down. What we have is we have three resistors that are in the circuit. This R3 is on a little rail, and we're going to pull it to the right. Okay, so we've got R1, R2, R3 in a circuit, and what we're going to eventually do is figure out the currents traveling through R1, R2, and R3. And we're not going to do the whole entire problem. I'm just going to show you how to set it up. Okay. Now, having said that, if this were it, okay. Oh, and by the way, this is L, the length between here, and this is V, the velocity with which I'm pulling R3. If this were it, there'd be no current flowing anywhere. Okay, so we're going to add some magnetic fields in here. Okay, so the first magnetic field, and again, make sure you have all this copied. So if you need to pause the video, go ahead. All right. So let's say this part of the circuit is immersed in a field that points out of the page. So I'll kind of draw that. We'll draw it as dots. Okay, we'll call that B1. Okay. Well, now we're talking. Now we'd have some current flowing. But we're not going to stop there, all right? We're going to also have, over here, we're going to have a solenoid. Okay, so imagine a ring pointed out at us. So here's a ring. That ring has some area A. There's a magnetic field in there that points into the page. I'll call that B2, okay? And let's assume that that is changing with time. And let's, for the sake of argument for right now, let's say that it's increasing with time. So maybe that's it's a top view of a solenoid, and you're increasing the current of the solenoid. So therefore, the magnetic field made by it is also increasing. So that X, we're getting more and more X's in that purple little area right there. Okay. So I'll make a little note. I'll just say B is getting bigger. Okay. Okay. So having said all that, well, now we're going to have some currents flowing in R1, R2, and R3. So our job is to find those currents. Well, in order to find those currents, we first need to find the voltages that are created by the following two things. Because this is a wire, a conductor moving through a magnetic field, there's going to be an EMF, a voltage generated, okay, a motional EMF. In addition, because there's a changing magnetic flux over here, you're going to get a voltage generated over there, okay? Now, how I suggest you do this is we're going to calculate those two voltages and then pretend like there are two little batteries in the circuit, okay? Because then that makes it a lot more manageable in solving for the currents. So let's start with R3 here. So R3 is moving to the right. If we imagine that I'm a little positive charge there, okay, and I do my Lorentz force rule, okay, among others. There's lots of ways to figure this out, but one way is to say, okay, if I'm a little charge there, I'm moving to the right, and again, I'm using force Lorentz is QV cross B, okay? Now again, there's several ways to figure this out. This is one of them, okay? But imagine I'm a little positive charge. I'm moving to the right, so that I use my hand to represent that, my fingers, and then I curl them in the direction of the magnetic field. My thumb represents the force acting on that positive charge. So that little positive charge is going to get driven down this way. That's as if there's a little battery over here, okay? And so I'm going to insert a pseudo battery here that points, the positive terminal points down, so it's going to look like that, and I'm going to call that E1. Okay, so there's our first, and again, it's not really a battery here, but it's as if there's a battery traveling with that thing, and it's pointed down, okay? What about this dude, okay? Well, he also makes a voltage. Now, conductors like magnetic flux to stay constant. If you change magnetic flux, the conductor will make a current such that it will try to oppose that change in flux. That's Lenz's law, okay? So within this rectangle right here, you've got an increasing field pointing into the page. Okay, so we're increasing the number of X's in that purple circle. This conductor, this whole thing actually says, I don't like that. I'm going to try to make a field pointing out of the page to cancel those additional X's that I'm trying to add. So as I try to add field pointing into the page, the conductors are going to make a field pointing out of the page. In order to make a field pointing out of the page, it's as if you've got a battery driving current counterclockwise through your circuit. Okay? So I'm going to put like a little battery, again a pseudo battery here, pointed down as well, because the current's going to try to go that way to counteract that change in flux. I'm going to make that E2. Okay? So imagine that that is E2. Okay? So now you've got a simple circuit. You got a circuit with 3 resistors and 2 batteries in it. Okay? So all you got to do is find the value of E1 and E2, and then you can solve for all the currents and such. So for each of those, and they're separate, for E1, okay, that's just this is this guy here. That's just a EMF generated by a conductor moving through a magnetic field. The equation for that is BLV. Okay, so E1 is simply B LV, and those are given, LV and then B. Oh, call that B1. Okay, so that's E1. So that's the value. If you were to actually calculate a number there, you'd put that little voltage right there for that battery. Okay, what about E2? Okay, well, E2. Okay, we're going to use Faraday's law, negative N d magnetic flux dt. Now, the negative sign we don't have to worry about here. We're just finding a magnitude. We already took care of that negative. That is Lenz's law, that little negative. And that just meant that as we added X's here, magnetic field into the page, the conductor is trying to make dots, which makes the current go that way. That's the whole negative thing, so we don't have to worry about that. N is 1. There's only one loop here. Okay, so it's just d flux dt. Magnetic flux is simply the integral, okay, of B dot dA. All right. Now, it turns out we don't have to really integrate. What area do we use here? Okay, well, you ask yourself, where within the conducting path is the flux or the magnetic field changing? Well, it's only changing in that purple circle. So you're going to use the area only of that purple circle. So that's your A, and that field is constant throughout that A, so you don't have to actually integrate here. So it's just B2 times that area. Boom, you're done. Okay, that goes in here, and then you're going to take, well, which of those two is changing with time? Is it B or is it A? Well, I told you that B is increasing with time. The area is not changing. So the EMF, okay, is simply, and again, I'm getting rid of the negative because I'm just looking for magnitude, is simply area times dB2 dt. So that's EMF number 2. Okay, that's your second little battery. So somehow I'd have to give you that area, like if we actually were doing values, I have to give you that area, I have to give you B as a function of time. You would take its derivative, multiply that by the area, and that value would be our little battery right here. Okay. Now once you have those batteries, the rest of this would be review for most of us. So now you got to draw, you got to use Kirchhoff's junction and loop rules to figure out what the currents are. So imagine, and you can make guesses here on which way the current's going to go. So for me, I mean, I would guess that I1, we'll call that I1, it probably goes that way. I2 or I3, I'll say, probably goes with that battery, so I'll call that I3. If those are actually accurate, I2 better darn well go that way. Now, and again, if you didn't guess right, all that would happen is when you do all the math, like let's say you guessed wrong on I3, for instance, if you do all the math, you'll just get a negative value. It's the right number, just its point is going the other way, okay? So then, what would you do there? Okay, so now we're using Kirchhoff's junction and loop rules. If I look at this junction, I would say that I2 equals I1 plus I3. So we got one equation, 3 unknowns. We need 2 more equations. Now I'll do this loop really quick. I'll start here, okay, and I'll go with the currents. So I'll go counterclockwise through that circuit. So starting there, I'm going with the current through R2, so it's going to be a negative voltage change or a voltage drop. I'm going with I1 through R1, so that's going to also be a voltage drop. It'll be negative in my equation. And then I'm going with the battery from the negative to the positive terminal, from the low to the high voltage. It'll be a positive voltage. So what would you write? You would write I2 negative times R2. That's the voltage drop that I2 encounters, minus the voltage drop of I1 going through R1, so I1, R1, plus, okay, E2 equals 0. And E2, you got that down here, whatever that number was, you would just stick that right there. So now we got a second equation. We still have 3 unknowns, so we need a third equation. So you pick a different loop. I will use, I'll use the right-hand loop, and I'll go clockwise through that, and I'll start here and go this way. So we go with I2 through R2, we have a voltage drop. We go with I3 through R3, that's a voltage drop. And then we go from the low to the high voltage part of that pseudo battery, so that's a positive voltage. So what would you write there? You'd write negative I2R2 minus I3R3 plus E1 equals 0. So if I gave you the values of R1, R2, R3, if you knew these values to plug in for E1, and if you knew this and B is a function of T down here, you could find E2. You'd have every number there but I1, I2, I3. You'd have 3 equations, 3 unknowns. In our class, we've discussed several ways to solve for multiple equations with multiple unknowns. So hope that was helpful. I will make a quick note. Take a hard problem and simplify it. So a moving wire through a magnetic field. It's like a little battery. So like pretend there's a battery there, right? When you have a changing magnetic flux over here, it makes an EMF. Pretend it's a little battery. All you got to do is figure out its value and which way to point it, okay? Then once you've done that, then you're just doing a Kirchhoff's junction and loop rule problem. So I hope that was helpful. Thank you very much.